Hello, my name is Harusuke Suge, and this is a joint work with Professor Tanaka of National Space Academy. Let's get started. First, I will show the background of my study. Hash-based signature schemes use only hash functions or block ciphers, and the schemes have these advantages and disadvantages. But the most important property is that they are post-quantum signatures. The security of the schemes is based on the security of hash functions or pseudorandom functions. And such cryptographic functions are believed to be secure against large-scale quantum computers in the future. And XMSS and XSMT, which are our target, have already been specified in RFC and NIST SP 800 series. And one of the hash-based signatures is XMSS. This is proposed by Böhmen, Dahmen, and Housing in 2011. I'd like to outline XMSS using this figure visually. In short, XMSS is a Markov tree using WhatsApp, and WhatsApp is a Wintonese one-time signature plus. As the name suggests, WhatsApp can sign only one message. WhatsApp can sign a message directly using the secret key of XMSS, and public key of WhatsApp is a leaf of Markov tree, and the root of Markov tree is the public key of XMSS. And signature consists of WhatsApp signature and authentication path, and the authentication path is a set of nodes required to compute the root from signature, like this. If a verifier can compute the root of Markov tree using signature correctly, this signature is verified. Once this WhatsApp is used, never use this again. Next time this WhatsApp is used to sign a message. And as you notice, the position of authentication path has changed a little bit. And signs again. And signs again. And false signatures have been generated and no more signature. And we should throw this key pair away. The number of signatures that XMSS can generate equals to the number of leaves. If the height of a tree is h, the number of signatures is to the power of h. In practice, we want more signatures, but more signatures indicate more leaf computations in key generation. A leaf computation is WhatsApp public key generation, and this is required. This computation requires more than 1,000 hash function codes. For this motivation, XMSSMT was proposed by Helsin, Rausch, and Bergman in 2013. The point is that key generation computes only the top tree, so the complexity is reduced from 2 to the power of h to 2 to the power of h divided by d, and d is the number of layers. In XMSMT, higher tree signs a root of lower tree, and the bottom tree signs a message. In the signature generation, an authentication path computation becomes a bottleneck because a node on height j requires 2 to the power of j leaf computations. And the complexity of the signature generation becomes exponential with the height of a tree if this scheme is naively implemented. So if the height is not as small as 5 or 10, the application area of XMSMT should be limited. And to solve this problem, we can use an algorithm called the BDS algorithm proposed by Behman, Dam, and Schneider in 2008. This algorithm can update the authentication path in linear time memory complexities. And the authentication path is stored in the state. I just explained about the procedure of the BDS algorithm using this figure. In this figure, all the colored nodes are in the state. In this figure, a leaf with thick line is the current leaf, and the authentication path for this leaf is expressed by red circles. In this step, this node should be kept in the state to compute a circled node in the future, because this node is required when the leaf index is here. The kept node is not in the authentication path anymore, so I change the color to magenta, but still in the state. Then circled node is computed by using kept nodes in the state, because this is going to be in the authentication path in the next step. This node is left child from his parent. In this way, left nodes are generated from kept nodes in the state with only one hash function call. Then look at this blue cycle node. This is a right node from his parent. Right nodes must be generated from scratch. For this node, we have to compute these two leaves. But the BDS algorithm takes a strategy to generate right nodes little by little, step by step. The computation is divided into multiple steps. In this step, only this node is generated and kept in the state. In this step, next leaf is generated and the cycle node is computed by these two nodes and kept in the state. Then the cycle node is in the authentication path now. Before it is required, the BDS algorithm can generate it and store it in the state. Generating the right nodes is the most complex part of this algorithm. In higher trees, multiple right nodes should be generated at the same time. This is very complex. The BDS algorithm is efficient, but it's hard to apply the algorithm to XMSMT for two reasons. First, each XMSS or tree is independent. Therefore, the BDS algorithm is applied to each XMSS, not as a whole. Second, once all signatures in XMSS are exhausted, there is a transition of XMSS occur like this. Exhausted tree is thrown away, never use this again, and new XMSS will be used to sign the next message. But how do you get this XMS ready to sign the next message, since it requires a state for the authentication path like this? The existing algorithm of HIP13 takes a strategy to initialize the next state while generating signature by the current state. Here we move to the motivation of our study. We'd like to improve a signature generation algorithm for XMSMT. There are two reasons. First, we want to reduce the state size. A state is stored in rewritable non-volatile memories. For some implementations, such as in smart cards, the state size can be a bottleneck because non-volatile memory is scarce. Especially in smart cards, non-volatile memory wears out if the memory usage is high. The existing algorithm of HRP13 stores two different types of states in every layer, except for the top one. Because of that, the state size becomes large. Second, we want to make the algorithm simpler. From the properties of XMSS and XMSMT, they are vulnerable to implementation bugs. The security of these schemes are based on the assumption that WordPress can sign a single message, never signs two different messages. For example, in XMSMT, a WordPress signs a public key of one lower XMSS. If this public key is computed from the state, the public key value may change because the state is changing data and the algorithm to compute the public key becomes very complex. Unfortunately, the BDS algorithm is a very complex algorithm, so we need to simplify the algorithm. From the motivation, we propose an algorithm. And this is the structure of the proposed algorithm. On the bottom layer, a modified BDS algorithm is used. As for higher layers, we propose a new algorithm. First, I modified the BDS algorithm. In existing algorithm of HRP13, two different types of states are used to generate authentication path without latency. On the other hand, our algorithm can generate the authentication path using only one state. This state can cover all trees on the same layer. From this, the state size becomes smaller and the state structure becomes simpler. Because the state of our algorithm is almost the same as the one for single tree. Also, I simplified two parts of the procedures to generate right nodes. As I mentioned in the explanation of the BTS algorithm, the procedure to generate right nodes is the most complex part. So it is important to simplify in order to simplify the BTS algorithm as a whole. In this presentation, because of the time restriction, I can't explain it, so see our paper if you're interested. We use the modified BDS algorithm on the bottom layer, but the BDS algorithm in general is of a spec on higher layers. Because signatures of trees on higher layers update only when the transition occurs on the bottom layer. While generating signatures, we can update the authentication path on higher layers. So memory efficiency is more important than time efficiency on higher layers. For this reason, we propose a new algorithm for higher layers. The algorithm is called MMT algorithm, and MMT stands for Memory Efficient Markov Tree Traversal. Here's an example. While generating signatures on the bottom layer, the next authentication path is stored in the stack. When this transition occurs on the bottom layer, the nodes popped from the stack to be substituted to the next authentication path. Very simple, but the state size is kind of minimal. At most, two authentication paths are stored in the state. I'd like to show how to apply the modified BDS and the MMT algorithms to XMSMT. On the bottom layer, we just use modified BDS algorithm. On higher layers, the MMT algorithm is used, but we want to minimize leaf computations on higher layers using this condition. I will show an example. Now a transition occurs on the bottom layer. So from the first condition, the authentication path on first layer is updated. Nodes on stacks are denoted by blue nodes, and these nodes are popped to be the part of the authentication path on the first layer. From the second condition, the state of this layer is updated. More specifically, this leaf node is generated, and using the next node, this node is computed and pushed on the stack. The point is that only one leaf computation is executed on higher layers. Last, I will show an analysis of the proposed algorithm. As you and I are cryptographers, we must be concerned about the security. In this study, side channel attack or implementation attack is out of scope, and such security evaluation is left as an open problem. But if we assume that the adversary can access only public key and the signatures, the security is the same. Because the formats of keys and signatures are the same, and the adversary cannot distinguish which algorithm was used to generate keys or signatures. So formally, the choice of algorithms has no impact on security. I compare performances and state sizes with existing algorithms of HIV-13. First, I compare signing time on average and worst case. As for the average case, they are the same. As for the worst case, our algorithm requires one more leaf computation than the existing algorithm. Next, I compare the state size in the table. Only the parameters whose security parameter is 32 bytes are shown in this presentation. As you see, that state size is almost half of the existing algorithm of HIV-13. So we implemented our signature generation algorithm using a reference implementation of RFC 8391. Actually, XMSS and XMSMT are specified in this RFC. And we confirm that our code is compatible with the reference implementation because the signatures generated by our code is correctly verified by the verification function of reference implementation. Also, we compare the performances of our code and their codes, and we confirm that they are the same. Also, we uploaded the reference, our implementation on GitHub. Conclusion. We proposed a new signature generation algorithm for XMSMT. On the bottom layer, we modified BDS algorithm, and the modified BDS algorithm is applied to simplify procedure and state structure. On higher layers, we proposed a new algorithm called MMT algorithm to reduce total state size. And we compare the proposed algorithm with the existing algorithm of HRB13. And we confirm that they have the same signing time on average. And the proposed algorithm has almost half state size. So we can reduce the state size without losing the performance by the proposed signature generation algorithm. That's all. Thank you for listening.